Good afternoon, everyone. Selamat datang semua. Shang Wu Hao, Varavarpu. Welcome to our third session of the 9-part T-Navigator Southeast Asia webinar series hosted by Rockflow Dynamics, Kuala Lumpur, and Jakarta. My name is Larissa Zimmer from RFD Kuala Lumpur, and today's session will be hosted by my colleague, Derek Ong, who is a reservoir engineer based in our Kuala Lumpur's office. Our R&D team would like to thank everyone who registered and allocated their time today to attend this webinars. Our team is working on the clock and will continue to provide our best support in this unprecedented time. Please do not hesitate to reach out to our support team for assistance. Before we begin, I'd like to provide a brief run-through on how to navigate yourself during this webinar session. Once you've logged on, you will be automatically muted, and should you have any questions in mind, kindly use the window in the control panel on the side of your screen and ask at the very end of this session. If we are unable to answer all questions live, don't worry, we will answer them afterwards and share it to you via email. All of our webinars will be recorded and uploaded onto our RFD Europe YouTube channel. Hence, feel free to watch them at your own free time. Last but not least, if you have any further inquiries, feel free to reach us at asktnav@rfdyn.com. A brief introduction about us. T-Navigator, developed by Rockflow Dynamics, was incepted in Moscow, Russia. It has been in development for the past 15 years, releasing 4 software updates per year, and is written in C++ and CUDA with over 4 million impressive codes. We're based worldwide with over 50 support engineers and geologists in 32 offices across 28 countries and over 100 software engineers supporting our development. And as of 2020, we are proud and humbled to have over 290 commercial clients in 42 countries and over 80 universities in 28 countries. We thank you for being with us. For today's topic, we're going to discuss on integration static and dynamic uncertainties for better prediction in T-Navigator. For the next up and coming 2 weeks, our Southeast Asia team will be discussing on some very interesting and in-depth topics, and we hope you'll find them insightful and educational. These webinar series will be hosted from one of our Southeast Asia offices. And for today's session, we're coming to you live from Kuala Lumpur, Malaysia. In today's webinar series, we will demonstrate you each stage of the integrated workflow that's available in T-Navigator. If you're interested to learn more on our modules, do not hesitate to get in touch with our teams, and we'd be more than happy to assist you. So, without further ado, let's begin today's webinar session. Thank you, Derek.
Well, thank you. It's Larissa. It's Derek here from RFD Kuala Lumpur. So I hoped everyone keeping healthy and active during this very interesting period. So thanks for your time for this webinar. Well, throughout the years of technical support and as well as involvement in the business development in the Southeast Asia, well, I can see that many asset team was trying to strategize and find ways to make this particular topic approach possible efficiently and be able to deliver within the FDP period. Well, some success, but what I see is that many of these workflow was poured to the drain even before the executions. And in this webinar, I would like to demonstrate that this objective can be achieved by making full use of the latest technology implementation in TNAV, which was currently aligned with Industrial Revolution. Well, just a bit of background. The level of uncertainty in the reservoir is significant in many cases. The infill development for one particular static model can have the best outcome, but at the same time, the same development can have the worst outcome in the other static model. And we all know that because different static model associated with different relations in the in-place distribution because each static model may have a different channel width, different variogram settings that leads to different phase shifts. Well, speaking from experience, and as well as I believe many of the audience here are aware that deterministic simulations model with a good history matching does not guarantee a good predictions. So here is how the integrated uncertainty quantification comes into the picture. So here in the integrated uncertainty approach, it is required to capture the unknowns in the reservoir, whether it's static or dynamic. Then we can proceed to do an uncertainty analysis, such as we can study the impact of the uncertainty parameters, which can be ranked. We can analyze the objective functions. We can quantify the possible range of the production outcome. So ultimately, by integrating the static uncertainty, it helps the reservoir engineer to quantify the modeling parameters on the geological site properly, and it helps to understand the reservoir characteristic to improve the quality of the well planning, optimize the production capabilities of the wells. Lastly, we can get a better representations of all possibility on whether you are working on production optimization or history matching. Well, actually many companies, as we are aware, are actually moving towards the probabilistic paradigm, but it has been challenging for many over the last several years because one basic thing that is required in order to work on this objective is to have a suitable applications. Well, which is usually bounded by several constraints. First, on the time. Well, integration between different departments, geo and engineering, takes time, especially if you are using an application that is not suitable or a lack of feature that they have the capability to integrate both static and dynamic together. On the pseudo integrations, some data may be lost by having different software platform, a different language between the G&G and RE. As we know, RE are interested into the history match quality, production optimization, while the G&G, they are more into the quantifying the in-place distributions for all the cases. And lastly, the ancient technology. For audience here, if you are still working on single core simulations or simulation using just CPU, I hope this webinar can give you a bit of different perspective towards what is the current available the technology for us to be utilized. And TNAV tackle all this challenge by having TNAV, which is provide scalability, which can handle large data, able to simulate well. On the integrations, it provides which I can say which is seamless because in the sense that it provides a simplified modeling workflow from variables definition to the uncertainty analysis. We will see more on that later on. Unified solution for multiple objectives. And lastly, parallel architecture, which means TNAV uses all core in your workstation, in your laptop, in your cluster by default without additional license required. And the last point is it uses GPU for simulation. Well, speaking on the last point, GPU, as we are aware, if we know more on that, otherwise we at least know that it has been in the industry for the last 10 or more years for this purpose. Have a look. Well, typically GPU, when emerged to the market, it is used to accelerate the frame rate quality, to refine the image quality, to ensure a very nice, amazing quality performance. But today, we are using this technology not just for gaming anymore. So starting from 2017, TNAV became the world's first reservoir simulations to support a hybrid of CPU plus a GPU for dynamic simulations. How is done? It's by handling the most compute-intensive part of the equations, which is a linear solver. And this part of the equation are split from the main equations and allocate itself to be handled by NVIDIA GPU alone. So the load sharing between the CPU and the GPU make a perfect sense to improve the performance up to 40 to 50% from CPU alone. And this study was actually conducted more than thousands of models worldwide. And I can say that this complex model that was tested include model from Petronas, PTTEP, Pertamina, Medco, Petrofac, etc. So, and from there, the technology evolutions continue over the last several years, and today, 2020, full GPU is now supported in T-Navigator, which means properties calculation, Jacobian, Newton, linear solver, and these are the core calculation that usually comprises of 80% of the runtime. And all these can be handled by GPU alone. Well, when we're talking about GPU in this particular webinar context, is because GPU in TNF, particularly for integrated uncertainty, is very important because the concern in this approach is not just limited to improving simulation time anymore. Because GPU, it helps to improve the overall experience in data loading, transition window, seismic processing, workflow computations, and if you have artificial intelligence or machine learning process in your workflow, is going to help to speed up the iterations. And all of it, we call it the big data analytics. So have a look at these animations. Well, if I'm working on a static model, I can integrate all the geological object, which is, for example, fault, horizons, grid, the seismic together, and I can ensure that the transitions is seamless. Here is an example that I'm working with 1,300 wells, a team that I was involved together with the geologists, each well associated with numerous well logs. And this application doesn't fail to impress me despite having such a big data. While on the dynamic side, parallel simulation, as I addressed, I believe existing users know that, real-time analysis where users are able to visualize the result in live, can control the simulation interactively, which means the user can start, modify, resume from the point of time where changes was made. So no time was wasted to the end before until the simulation is completed. So when I'm working on the uncertainty analysis project, definitely I am dealing with a large amount of data, whether it's static or dynamic, and uncertainty in structure, diagrams, interpolations for facies, perm, etc. Well, here is where I can throw all of these variables into TNF and let the uncertainty module in TNF do the work for me. Here is where I can choose algorithm, whether it's experiment design or optimizations. Depends on my goal. If I can choose whether I want to optimize my in place or my my well control or predictions. Here is where the big data analytics interface for me to analyze my results. And I can say the key to make this seamless experience is the key is to have the integrate and the unified interface. And here is a diagram of what I'm saying. Well, a bit of background. A geology designer, if you haven't used it, is a complete static modeling package with geophysics capability, while model designer is an engineer tool to initialize a static model to dynamic model by input your properties and development strategies. Well, what if a geologist had not been using TNF, is using the other applications? But no worry, because TNF can bring in geo data easily from the other application using what you see here, TNF plugin, or a more convenient options will be Rescue, and Rescue ML is going to implement it this year. But as a RE, when I'm going to do this integrated approach for uncertainty project, I got to make sure all static objects are original. I can keep track of the object modifications history that was previously done by my Geo colleague. And the good news is, Geo designer and the model designer, they are sharing the exact same interface to ensure the RE can adopt a Geo model without conversion required. I have the full accessibility to all the Geo parameters, including the variogram settings, interpolation type settings. I think that is all important because we are going to have all of that in our control to do the big data analysis in terms of uncertainty analysis from the Geo to the dynamic part. So I can say that this interface was really optimized for both RE and geologists to work together. So it provides a single environment for seismic, geology, RE, PVT, wellbore and surface network modeling. This actually encouraged there should be no time wasted or data lost by moving between the applications. So because all this process is being automated by the automated workflow. Well, speaking of the workflow, it usually comprises of two steps. First, define variables in the workflow. Second, run uncertainty analysis. From the RE perspective, which RE usually work on a dynamic model. Having a geology designer license in the model designer is like giving me a full-fledged access to all geological objects, like the horizons, well logs, seismic, well tops, because I would like to have all of those as my uncertainty variables. And all this can be done within the workflow. So one of the current technology revolution in the software or many software in general, particularly in TNF, is to allow the user to input their programming language code to integrate with the software, right? So what makes workflow in TNF more powerful or more capability compared to the others is that at the background of the workflow is powered by the Python. So user doesn't have to install the Python, and they can actually use Python for simple coding and for reading. So for anyone who doesn't know Python like myself, I don't really master Python. No worry, I can guarantee you that whatever is available in the workflow, it already has a full-fledged options from import interpolations or input a calculator. Pretty much all the feature it is already in the workflow. I'm just saying that if you know Python, you are like in the God mode, which you can do. You can input your code to design a well trajectory or conversion optimizations, just for example. Well, in this workflow is where we define the variables. So this is a model that replicates a fluid environment. So here, example, we have a structural uncertainty where we adjust the horizon depth by maintaining the grid cell, which will give me a different volume while maintain the grid cells. So geostatistical. So as we know, if we are working only on the data deck, which means the dynamic model only, we have a limitation in certain static parameters that cannot be changed. For example, we can change the porosity by a multiplier in the equations, or we can extend the multiplier by region, but we cannot change the channel directions, phases, distributions. But here is everything is possible. Well, geostatistical uncertainty here, I have an example of having my variance range, sit, and my azimuth, which I will control the output of different phases, channel, crevasse play, that would control my phases distribution later on. And I also have the Poropom transform where I have the variables that is defined within the equations. Dynamic uncertainty. Here, I believe most of the most of the audience here are RE. We are familiar with what we can do. So here is just a very simple examples of context RP endpoint. We have the correlations uncertainty. Of course, the other thing that is not shown here, like infill well control, correlation interval, all those can be part of the uncertainty as well. And once we have defined the uncertainty, then we can submit it for our uncertainty module in T-Navigator. So note that all of this is being done in one software, which is T-Navigator. So here is in the AHM uncertainty, here is where we make evaluations for thousands of models, a log analyze of all realization as one big data. Let's have a look at how it's like. Okay, so this is the main interface. It uses all core by default. I usually prefer the dark theme because it has this kind of elegant look. Well, next, I would like to select the GPU. So it's very easy because TNF automatically detects the GPU in your workstation. I just need to put a checkbox next to the use GPU. So as I mentioned again, it's a unified interface of a geo and a model designer. So it doesn't matter where do you open it, as long as you have a feature for both or you have license for both. Here, I am going to create a new project which doesn't have anything. Okay, I just create a new project here. In seconds, I will have my empty project. So I can choose to import the object one by one, or I want to speed up the process here. So I go to the workflow where I have a previously built workflow that I would like to import. So this workflow comprises of the object import, which include my well trajectory. I think it's about 40 wells, 10 different well logs for each wells. I have my last file, horizon file, as well as my property interpolations, all the way until dynamic model building. I'm going to go through that later on. So here I'm going to press on the test button just to make sure all the input are right before I run the workflow. So as you can see, it's in green, which means this, whatever is defined in the workflow in the process, is all good to go. So now I'm going to press the big button called the run workflow. So when I'm running, I am going to minimize my workflow. As you can see at the back, it's happened concurrently. So as you can see, my workflow is running. At the background, it generates what is being told within the workflow. It creates a horizon bounded by the well tops, top and bottom reservoir. It generates the structure with grid, import the fault. It produces the properties based on my varograms and interpolation methods, as well as my fluid properties as well. Okay, let me close the window of my workflow so that I can see a full view of what I have in the interface. I'm going to minimize it. So, well, everyone can see what we have here in the 3D. Okay, I'm going to the fluid properties. Here in my workflow, I have defined the PBT, RP, and basically the basic thing that I have. If I would like to model more things, I can always go to more properties to model EOR, compositionals, or advanced function like J functions. All is available. But I'm going to go with the simple model. Here is where I have my PBT. It's integrated with a PBT designer, which we can do EOS or colorations. Well, I have the RP, which I can visualize multiple relative permeability. In this case, I have RP by Corey correlations. I have the context, the rock information. Now, what if I'm new to simulations? I would like to know more info about relative permeability, for instance. So pay attention to the right corner bottom. There is a question mark, and if you bring directly to the user manual that shows me that particular information, I personally find it very useful despite using TNet for many years. Okay, let's move on to well data. Here is where I have defined the strategies, well rules, and time steps. Data analysis is more for a GNG, but here I can visualize my varograms, ranges, azimuth. Let's go back to the geometry object. So as part of my workflow, I also initialize the model already as part of my workflow. As you can see, without simulation run, I already can visualize my fluid in place. I can show my property statistic that shows me the informations. I personally find it very useful because I don't have to run the model, but I already have access to the fluid in place. And as you can see, the box is reflect to the property that I'm standing. Right now, I would like to run simulation just to give everyone a perspective how it's like. Can I work along the model while the model is running? The answer is yes. So as you can see, while my model is running, I can do a lot of things. For example, I can adjust my interface so that I can visualize several tapped 3D cross sections, well section at one go. Whatever property is showing, it is showing in real-time results. Aside from the 3D display, I would like to visualize the graph as well. So in the graph, as you can see, it is a real-time result. It produces the graph up to the time step it is calculated. So this is very useful personally as RE as well. So the one in the dotted line is my historical data, and my calculated is presented by the bold line, sorry, the solid line. Well, the objective of this webinar is not really to show on this particular feature. It's just something extra I would like to show. But the main goal is how we can adjust the variables and then we run the cases in the big data. So just give me a few more seconds and then we go back to the geometry object. Okay, in the geometry object, here is my my horizon. I would like to play with the depth of my horizon as part of my uncertainty for my structure. We go to the workflow. So here is where we define the variables. I like to give you a name called structural horizon. Any name would do, with an uncertainty of plus minus 10 meter. Okay, and I will assign these variables to that particular process, which is here. This is called the horizon calculator. Then I can assign the variables over here. It's very easy to do. And I would like to do the same for my varograms. I would like to define the ranges for my, for the uncertainty for my mean range, vertical range, and my azimuth. And again, we go back to the workflow to do the same purpose. But to cut the time short, I already have the variables that I have properly defined or parameters. So as you can see, I have the variables for my diagrams is properly defined. Instead of the number, I define a name itself. So this is for my diagrams that it will change my phase distribution later on that affect my poro and permeability. So in my perm X and my perm Z, I also have my uncertainty in the equation itself. Dynamic part, I'm going to do something very simplistic. For example, I define two variables inside the Corey colorations. So now the next big thing is here. How do we define it? How do we launch uncertainty project? So pay attention to the button on the top. TNAV designed the button so that it's easy to guide the user. What are they going to do next? So you can see a magic wand button, which is just right next to the workflow. It actually helps me to know, okay, that is what I'm going to do next. So I press on OK or Enter. So just give it a few seconds. It is going to open the AHM project. So here is an interface where I can choose to do external design or optimization. In this case, I'm going to do a Latin hypercube sensitivity analysis. Right, then I define the number of cases that I would like to launch, and then I just press on Enter. And basically we are done. We come back over a cup of coffee, or we can take a look what we have here. Project info shows me all the basic info that I need to know. The type of experiment, the variables that I have, and what are the distribution of each variables for each cases. In the calculation tab, it shows me the status of the current run. If you queue one by one, or if you can choose to run multiple cases at one go. Well, now to cut the time short, I already have a project completed Latin hypercube. I would like to open it here. Okay. So as you can see, it's already completed run, except two more cases. But without waiting on those two cases, let's go to the result tab on the bottom left corner. Let's press on the result. So here, I usually like to call it the big data analytics platform because it gives me all the results that I want to see in one place. For example, in the graph, I can see the oil total, what are the possible ranges that I have of all 100 cases. The one in the dotted line is my historical data. Then look at the water total, okay, larger possibility, and here is where I need to optimize my water total. So let's go to objective function for this purpose. Because we want to optimize two object parameters here, which is my oil rate, water rate. So I need to create a new objective function, which I have a simplistic approach, which is I define my oil rate in the field level and my water rate at the field level for these objective functions. So in no time, my objective function is ready. I can see it in my table tab, which I can sort based on descending order, which the descending order, I can visualize it in the cross plot. As you can see, for both oil rate and water rate, the mismatch was reduced over time. Well, the main thing about the data analytics here is the analysis tab, which shows me the P10, 50, 90 cases. What are the values for each parameters? If I'm interested in the oil in place, I can take a look here. Or I want to visualize the value in the P25, which is not here. I can easily add it here as well. So this is how easy we can do it. Simply add on it with no time. Now I want to translate this into the CDF so that I can see a curve of my oil in place or any parameters I am interested in. Well, next question you may be asking, how do I visualize the distribution of my variables, which is not too close between two cases? Here I have a histogram, which I can see, can select the cases that I would like to see. I can see that the distribution of each variable are equal, right? Okay, let's come back to CDF. There are several things that we can do here. For example, prediction mode or further optimize my historical data. Here, I would like to show an example. I would like to optimize my history matching for my P10 5090 model by simply click on the cases. As you can see in my model list, I have 3 cases is now being selected. I can right click. I say I want to create new experiment, which is my optimizations. I only optimize based on these 3 cases. So here I have a choices. I would like to select PSO as my algorithm and select the objective function, which is the same as before, oil rate and water rate. Well, before optimization, I have another options to go, which is, as you can see, I have several variables. So I would like to check if all the variables actually impact my results or not. So with these options, we can go into Pareto chart. So as you can see in the Pareto chart, I can see the impact of each variable towards my objective function. This is very useful because we do not want to waste the runtime resources on the parameter that it doesn't impact. In this case, I can see that my main range variables and my azimuth variables, it doesn't really impact very much on my objective function compared to the rest. So I do not want to waste my optimization resources onto these 2 variables. So I uncheck both of them. And so my optimization can focus on the rest of the variables. Let's click on OK. And again, we can go to Configure again because now PSO job is currently on the go, which we can see it under calculations. Well, again, to cut the simulation time short, so I have a ready project that I'd like to show you. Okay, so let's go back to the designer interface, which I will open up the completed uncertainty cases. So as you can see, just give me a few more seconds. So this is the same interface with a completed runs, which I have modified the tab a bit, which is customizable. I would like to, what I'm going to do here is in the table tab, I will sort my objective function again so that I can see my cross plot that is constantly reduced in terms of the mismatch over the cases. And this, I have the oil mismatch. On the right corner, I have a stack plot that shows me objective investment, which means those oil rate and water rate in my objective function, I know which parameter actually contribute to the large values of objective function. In this case, I know that water rate is the one that I really need to focus on. Well, graph on the top, it shows me the oil possibility. And the bottom, I have the Pareto chart again. It shows me the impact of each variables towards my objective functions. And also on my top right corner, I have my CDF again, which shows me my quantile distributions. Give me an idea what is the range of P10 to P90 among 1,000 of cases here. So there are 1,000 of cases, and here is how easy we can integrate all informations and to see it at one go. Well, to summarize everything here, I want to say that your model is already complex. Well, it may be even more complex if you're working on a complicated interface that filled with hundreds of buttons, which we don't need. Well, honest opinion, I think TNF has a straightforward interface and also the integrated workflow that make full use of the integrated interface, GPU, Python code, and it produces a straightforward large data platform for us to analyze thousands of realizations by integrating both static and dynamic together. And then we can use this, what you see here, for decision making. Well, I really hope that this webinar can inspire all of us as a geologist, RE, or management on integrated approach. It can be simplified. Yeah, so I really hope you enjoy the sessions, and I hand the floor back to Larissa to open up the questions. Thank you.
All right. Thank you, Derek. That was a very, very colorful presentation. Okay, so thank you to all attendees. So as mentioned by Derek, we have the floor open now for all incoming questions. And let's see what questions we have. So question number 1, Derek. How complex can TNAV handle in terms of wells and original model without upscaling for uncertainty analysis?
Yeah, well, that was a great question because TNAV, when we developed since day one, we don't encourage upscaling. Of course, we have the options, but we don't encourage upscaling because the TNAV itself, it can handle very fine scale, complex model. Like what we shown earlier here is that we have 1,300 wells. It can correlate seamlessly. At the same time, we have a case study of 13.6 million active cells, and that is, I think, one of the record active cells. So I hope any company would like to challenge that. I hope I can be part of the game. All right.
Cool. Very, very interesting. Second question. Can I use this integrated approach for better prediction optimization instead of history matching optimization?
Yes, definitely yes, because what we see as a demo here is just for history matching. But of course, like I mentioned, you can do other things as well. For example, I can proceed with what we have here to do prediction optimizations, which you can load the results. I mean, you can use the prediction well to optimize where is the best well locations for my future wells, for instance. So yeah, it's possible. Yes.
Okay. Last but not least, as you mentioned earlier, GPU can be used for both improving transition experience in displaying 3D objects like well and seismic. I'm interested in getting a GPU for my subsurface team. How much can a GPU improve simulation time compared to without GPU? Are there any statistics for this?
Yes, definitely. We have a statistics of, I can say, 1,000 cases, and the number is growing. So 1,000 real and complex model worldwide. That include the model from Petronas, PTP, and any company worldwide. So the improvement compared to only CPU is ranges from 20 to 40%. Of course, I have to mention that it really depends on your model complexity. The more complex is your model, the more wells, the more contrast in your properties, the more benefit that you get from the GPU card. Of course, we're open to the benchmarking if I like to do to get an assurance on the performance using a GPU. Yeah.
All right, great. Thank you so much, Derek. And thank you to all attendees for the questions. Please feel free to include all the remaining questions. We will leave the webinar open for the next few minutes. And we will address them accordingly after this webinar session and personally email it to you. If you'd like to watch this session, you can find all of our webinar materials on our RFD Europe YouTube channel. Make sure to catch our next webinar session Monday next week at 2:30 p.m. Malaysian timing, hosted by our Jakarta's office. Again, we thank you everyone for joining today's session. There will be a short survey for you to provide your comments at the very end of this, and we welcome any feedback. Till then, we hope you enjoyed the session and we look forward to seeing you Monday next week. Take care and stay safe. Sekian, terima kasih.